The concept of wormholes and their potential to allow travel into the past has always been a subject of fascination and speculation. However, it is crucial to acknowledge that wormholes are inherently unstable. Despite the proposition of exotic stabilization schemes, there is currently no evidence to support the feasibility of these methods, nor is there concrete proof of the existence of wormholes themselves. This starkly highlights the gap between theoretical conjecture and empirical verification within the realm of modern physics. In an intriguing development, the wormhole C metric, a solution of Einstein's field equation coupled with a phantom scalar field, has been identified. This solution describes accelerated wormholes and represents a significant departure from conventional theories. Notably, in certain parameter ranges, this solution does not possess any horizon, distinguishing it as a viable candidate for a wormhole. Furthermore, the spacetime outlined by this solution lacks photon orbits, consequently resulting in the absence of a shadow. This characteristic deviates from traditional spacetime solutions and presents a novel aspect for potential observational detection. The C metric, characterized by a pair of causally disconnected black holes with uniform acceleration, falls under the general class of Plebinsky-Demiansky spacetimes. The acceleration of these black holes is attributed to either a conical deficit angle along the symmetry axis or a strut with negative tension developing between the two black holes. This theoretical framework has proven instrumental in modeling accelerated black holes and provides insights into binary black hole mergers and gravitational radiation. The accelerated version of wormholes, introduced through the analytic continuation of a parameter family of the gauge supergravity, emerges as a solution of Einstein's gravity coupled with a phantom scalar field. This solution, expressing a transition to a different family of C metrics, converges towards wormhole solutions in the zero acceleration limit. An essential attribute of these C metrics is their ability to circumvent the conical singularities typically required for inducing acceleration, solely facilitated by the phantom character associated with the scalar field. The investigation into the geodesics and quasi-normal behavior of the wormhole C metric offers valuable insights for potential observational imprints. Notably, the absence of a shadow in the spacetime under consideration is a distinctive feature that sets it apart from previously known solutions. This absence may reveal intriguing observational aspects and serve as a probe for validating underlying quantum gravity theories. Moreover, the stability of spacetime against perturbations is a critical area of study, particularly in the context of black holes and the emission of gravitational waves during binary mergers. The exploration of quasi-normal modes, QNMs, in this spacetime and the effects of boundary conditions on these QNMs sheds light on the dynamic behavior of spacetime under external perturbations. Interestingly, it was found that the spacetime tends to retain excitation following perturbation, a phenomenon that demands further theoretical and observational attention. In summary, while the theoretical foundation of wormholes presents a tantalizing prospect for time travel and interstellar journeys, the empirical evidence remains elusive. The study of the wormhole C metric and its unique properties, however, opens new avenues for understanding spacetime and gravity, marking a significant step forward in the quest to unravel the mysteries of the cosmos. The exploration of wormholes extends beyond the domain of theoretical physics into the realm of science fiction, where they are often portrayed as gateways to distant universes or conduits for time travel. This portrayal feeds into the collective imagination, painting a picture of wormholes as cosmic shortcuts that could one day revolutionize space exploration and even alter our understanding of time itself. However, the transition from the fictional narrative to the scientific reality of wormholes reveals a complex and challenging landscape. At the heart of the scientific investigation into wormholes is the recognition of their intrinsic instability. This instability poses a formidable obstacle, rendering the practical realization of wormholes, as often depicted in science fiction, a distant prospect. Scientists have proposed various exotic stabilization schemes in an attempt to address this inherent instability. These schemes typically involve the use of hypothetical forms of matter with negative energy density, known as exotic matter. Exotic matter is theorized to counteract the gravitational forces that would naturally cause a wormhole to collapse, thereby keeping it open and traversable. Despite these theoretical advances, the stabilizing mechanisms remain purely speculative, primarily due to the lack of empirical evidence supporting the existence of wormholes. The scientific community has yet to observe a wormhole directly or indirectly, leaving the concept firmly within the realm of theoretical physics. This absence of concrete evidence underscores a significant gap between the imaginative allure of wormholes and the current scientific understanding of their nature and properties. The speculative nature of stabilization mechanisms further complicates the already challenging endeavor of bridging the gap between theory and reality. The requirements for stabilizing a wormhole not only challenge our current understanding of physics, but also raise questions about the feasibility of creating or discovering such exotic matter in the quantities necessary for wormhole stabilization. The exploration of wormholes, therefore, remains a complex interplay between theoretical speculation and the pursuit of empirical evidence. While the concept of wormholes captivates the imagination and stimulates scientific inquiry, it also highlights the limitations of our current understanding and the vast unknowns that lie ahead. The journey from the speculative theories of wormholes to tangible evidence and practical applications is fraught with challenges, underscoring the need for continued research and exploration in this enigmatic area of physics. The discovery of the wormhole C-metric, a novel solution to Einstein's field equations coupled with a phantom scalar field, marks a pivotal advancement in the study of wormholes. This groundbreaking solution describes accelerated wormholes, distinguishing itself from previous theoretical models by challenging the conventional belief in the necessity of exotic matter for the support and stabilization of wormhole structures. Instead, the wormhole C-metric introduces a paradigm shift, suggesting that certain configurations of spacetime, facilitated by a phantom scalar field, can inherently possess the stability required for a wormhole to exist without collapsing. The implications of this finding are profound, opening new avenues for understanding the fabric of spacetime and the fundamental forces that govern the universe. The phantom scalar field, a hypothetical field with unusual properties, including negative energy density, plays a crucial role in this solution. It provides the necessary counterbalance to gravitational forces that would otherwise cause a wormhole to collapse, thereby offering a theoretical framework for stable, traversable wormholes without relying on exotic matter. One of the most intriguing aspects of the wormhole C-metric is its avoidance of horizons and photon orbits within certain parameter ranges. Traditionally, the presence of horizons and photon orbits has been a defining characteristic of celestial objects like black holes, influencing how these objects interact with their surroundings, including light. The absence of horizons and photon orbits in the wormhole C-metric suggests that these wormholes would not cast a shadow, a feature that starkly contrasts with the expected behavior of many cosmic structures. This unique property could have far-reaching implications for observational astronomy. The search for wormholes to date has been largely theoretical, hindered by the lack of distinctive observational signatures. The wormhole C-metric's lack of a shadow presents a potential observational hallmark that could aid astronomers in the detection and study of these enigmatic structures. By refining our observational techniques and focusing on the absence of expected shadows, scientists may be able to identify the presence of wormholes within the cosmos, offering unprecedented insights into their properties and behaviors. Moreover, the wormhole C-metric challenges and enriches our understanding of gravity and spacetime. By illustrating that accelerated wormholes can theoretically exist without exotic matter, this solution encourages a reevaluation of the underlying principles of general relativity and quantum field theory. It prompts questions about the nature of spacetime, the distribution and behavior of matter and energy within the universe, and the potential connections between disparate regions of the cosmos. In summary, the discovery of the wormhole C-metric represents a significant leap forward in the study of wormholes and their implications for physics and cosmology. By challenging previous notions and introducing new theoretical possibilities, this solution not only expands our understanding of wormholes, but also invites further exploration into the fundamental structure of the universe. As research continues, the wormhole C metric may pave the way for groundbreaking discoveries that reshape our conception of the universe and our place within it. Embarking on a cosmic journey beyond the confines of the solar system opens up a vista into the enigmatic realm of extrasolar planets. These planetary bodies, bound by gravity to stars other than the Sun, were cast into the spotlight with the first discovery in 1992. To date, more than 5,000 extrasolar planets have been confirmed, and nearly 9,000 more are on the cusp of validation. The pioneering detection of planets beyond the solar system began with the pulsar planets of PSR 125712. This breakthrough was achieved using pulsation timing, a method that measures the periodic signals emitted by pulsars, rotating, magnetized neutron stars. This technique is so sensitive that it can detect motions induced by planets with masses as minor as Earth's moon. Microlensing, another ingenious detection method, takes advantage of the gravitational bending of light, as predicted by Einstein's general theory of relativity. It is adept at identifying massive planets orbiting at vast distances from their stars, and has even unveiled a group of free-floating giant planets that are not anchored to any star. Direct imaging, which captures light reflected off a planet or the thermal infrared radiation it emits, has proven effective for planets circling the Sun's nearest stars. Young, massive planets that lie far from their stars are especially susceptible to detection via infrared imaging due to their substantial heat signatures. Complementing these methods is transit photometry, which measures the diminution in starlight when a planet moves between its star and the telescope. This not only reveals the size and orbit of the planet, but also, when amalgamated with radial velocity data, discloses precise mass and density, offering insights into the planet's composition. Spectroscopy, which assesses changes in the depth of transits across different wavelengths, has identified water, hydrogen, sodium, and methane in the atmospheres of some proximate giant planets. The James Webb Space Telescope's study of WASP 96b spectrum as the planet transited its star is a testament to the power of these combined methods. At approximately 1,150 light-years from Earth, WASP 96b's spectrum exhibited a clear signature of water and provided evidence for atmospheric clouds and haze with a mass about half that of Jupiter. Despite these advancements, extrasolar planets remain challenging to detect directly due to their faintness compared to the stars they orbit. The most fruitful technique to date remains the radial velocity method, which discerns the motion of stars under the gravitational influence of orbiting planets. This method not only determines the orbit sizes and shapes, but also sets lower mass limits for the detected planets. The physical properties of extrasolar planets reveal a startling diversity. Surveys indicate that between 5 and 10% of stars host giant planets 100 times Earth's mass or more, with some in exceedingly close orbits that have distended them due to stellar heat. Over 20% of stars possess smaller nearby planets, with masses ranging from several to tens of times that of Earth. The composition of the most massive transiting planets is dominated by hydrogen and helium, similar to the solar system's giants, Jupiter and Saturn. The terms Jupiters and hot Jupiters have emerged to describe worlds that are massive and in close proximity to their stars, respectively. Meanwhile, Neptunes and super-Earths denote smaller, potentially rocky planets, some of which may harbor heavier elements in greater proportions. Yet many properties of these extrasolar planets contrast sharply with our solar system's architecture. For instance, within the solar system, the planets, especially the larger ones, have nearly circular orbits. However, many extrasolar giant planets with longer orbital periods possess markedly elongated orbits, suggesting dynamic histories involving migration and gravitational interactions. Stars with a higher percentage of heavy elements are more prone to hosting gas giant planets, and stars in binary systems are frequently found with multiple detectable planets. The range of mass for these exoplanets is vast, extending from nearly twice to thousands of times that of Earth. While the current detections skew towards larger, potentially life-inhospitable planets, This bias is a product of detection capabilities rather than an indication of their prevalence in the cosmos. This intriguing assortment of characteristics among extrasolar planets not only broadens the understanding of planetary systems, but also invites contemplation on the conditions conducive to life beyond the familiar borders of the solar system. Turning to the challenge of detecting extrasolar planets, the pursuit to unveil these invisible worlds is a testament to human ingenuity and technological prowess. The radial velocity method stands as a cornerstone in this scientific endeavor. This technique measures the subtle wobble of a star induced by the gravitational pull of an orbiting planet. It was this method that led to the historic discovery of 51 Pegasi b, a breakthrough that earned Michel Mayor and Didier Queloz the Nobel Prize in Physics in 2019. The detection arsenal extends beyond radial velocity. Pulsation timing, for example, examines the arrival times of signals from pulsars and has the finesse to detect planets with minuscule masses. Microlensing, on the other hand, uses the gravitational lensing effect to find planets at great distances from their host stars, revealing even rogue planets that drift through the galaxy unattached to a star. Direct imaging, while challenging due to the brightness of stars compared to their planets, can capture actual visual evidence of planets, particularly those that are young and massive, orbiting at considerable distances. Transit photometry has revolutionized the field by detecting the minute dip in brightness as a planet passes in front of its star. This method not only ascertains the size and orbit of the planet, but also, when synergized with radial velocity measurements, affords the calculation of the planet's mass and offers clues to its composition. Such data have allowed astronomers to detect the presence of various gases in planet atmospheres, taking the understanding of these distant worlds to new heights. The James Webb Space Telescope has pushed the boundaries of what was previously possible, capturing the spectrum of WASP 96b with precision and revealing water signatures, clouds, and haze in the atmosphere of an extrasolar planet. These observations are groundbreaking. They provide a window into the atmospheric conditions of planets hundreds of light years away. Each method plays a crucial role in the ongoing quest to map the celestial bodies that populate the galaxy. The combined efforts and technologies not only pinpoint the locations of these planets, but also peel back the layers of mystery that have shrouded them, slowly shedding light on the nature of planets that exist beyond the solar neighborhood. The catalog of extrasolar planets is ever expanding, and with it, the knowledge of the vast and varied universe that awaits further exploration. The astonishing variety of extrasolar planets challenges preconceived notions of planetary formation and composition that have long been based on the solar system. The diversity extends from colossal gas giants, many times Earth's mass, to smaller, potentially rocky worlds dubbed super-Earths. These discoveries have prompted a reassessment of the mechanisms that govern planet creation. One of the more surprising characteristics of extrasolar planets is their often elongated orbits. In stark contrast to the nearly circular orbits of the solar system, many of these distant worlds travel on paths that bring them in close, searing proximity to their stars. These conditions have led to the classification of hot Jupiters, gas giants that orbit so near their stars that their atmospheres can reach extreme temperatures, causing them to bloat in size. The discovery of hot Jupiters and other exoplanets has profound implications for the understanding of planetary systems. It suggests that dynamic processes, potentially involving gravitational interactions and migrations, play a significant role in planetary system evolution. Furthermore, the existence of such planets challenges theories on the potential for life beyond Earth, as the conditions on these worlds are vastly different from the life-supporting environment of Earth. There is also a fascinating link between stars that are rich in heavy elements and the likelihood of hosting detectable gas giant planets. This correlation suggests that a star's chemical composition influences the type and size of the planets that can form within its system. The presence of heavy elements may increase the efficiency of planet formation, leading to the development of sizable gas giants. Additionally, the concept of free-floating planets, unbound by the gravitational pull of any star, expands the boundaries of what is considered a planetary system. These rogue planets wander through the galaxy in solitude, raising questions about their origins and the diversity of planetary existence. The continuous study of extrasolar planets not only enriches the understanding of the cosmos, but also underscores the complexity and variability of planetary systems. It opens the door to contemplating the existence of other worlds that may harbor life, expanding the search for biological signatures beyond the familiar confines of the solar system. As the exploration of these distant planets progresses, the knowledge of the universe's vastness and the place within it continues to evolve. The Physics of the Cosmos program, nestled within NASA's Astrophysics division, serves as a conduit between the realms of physics and astronomy, endeavoring to unravel some of the universe's most fundamental mysteries. This includes probing the veracity of Einstein's general theory of relativity, understanding the behavior of matter and energy in extreme environments, discerning the cosmological parameters that governed the universe's inflation and its ongoing evolution, and uncovering the true nature of dark matter and dark energy. Situated at the Goddard Space Flight Center, the program oversees a variety of missions and technologies aimed at shedding light on these profound questions. Integral to the program's operation is the facilitation of the PhysCos Program Analysis Group, which encompasses science interest groups engaged in high-energy astrophysics-specific branches, alongside science analysis groups tasked with exploring pertinent science and technology topics. This structure ensures a focused and collaborative approach to understanding the cosmos physics. Moreover, the program plays a pivotal role in identifying and prioritizing technology gaps that, once bridged, could significantly enhance future astrophysics missions with implications for PhysCos science. This prioritization process informs strategic decisions regarding technology development, thereby advancing the field's frontiers. Among the program's highlighted endeavors is the collaboration on the XR-ESM, X-ray Imaging and Spectroscopy mission with the Japan Aerospace Exploration Agency, JAXA. This mission, among others, exemplifies the program's commitment to international collaboration in pursuing scientific excellence. On a parallel front, the International Center for Quantum Field Measurement Systems for Studies of the Universe and Particles, QUP, exemplifies global efforts to advance our understanding of the universe. By participating in the Science and Technology Pre-Event 2024, QP demonstrates its commitment to community engagement and education, showcasing cutting-edge technologies and scientific achievements. Dr. Kosuke Itabashi's discussion on radiation-hard semiconductors highlights the innovative research conducted at QUP, further emphasizing the importance of technology in unraveling the cosmos secrets. The exploration of dark matter and dark energy represents another frontier in our quest to understand the universe. These enigmatic forces, invisible yet omnipresent, dictate the structure and fate of the cosmos. Despite their elusive nature, ongoing research endeavors aim to illuminate their properties and mechanisms, promising to significantly advance our cosmic understanding. As these efforts unfold, the future of inflationary cosmology research looms large, promising to delve deeper into the universe's origins and evolution. By harnessing advanced observational techniques, refining theoretical models, and fostering international collaboration, the scientific community stands on the cusp of groundbreaking discoveries that could redefine our understanding of the cosmos. In the early 1980s, physicist Alan Guth introduced a concept that would revolutionize our understanding of the universe's infancy. This concept, known as inflationary cosmology, posited a period of exponential expansion that the universe underwent fractions of a second after the Big Bang. This rapid expansion, according to Guth, could provide answers to some of the most perplexing mysteries surrounding the early universe. One of the most compelling pieces of evidence supporting the Big Bang theory was the discovery of the cosmic microwave background radiation. This radiation, a relic from the early universe, is remarkably uniform across the sky. However, this uniformity presented a conundrum. Without a mechanism like inflation, it was difficult to explain how regions of the universe, now billions of light years apart, could have once been in thermal equilibrium, given the speed of light and the age of the universe. Inflation elegantly resolves this issue by proposing a rapid expansion that stretched the universe far beyond its original dimensions, thus ensuring the observed uniformity of the CMB. Furthermore, the theory of inflationary cosmology provides an explanation for the large-scale structure of the universe, including the formation of galaxies and galaxy clusters. During inflation, quantum fluctuations in the fabric of spacetime would have been amplified to macroscopic scales. These fluctuations later served as the seeds around which matter coalesced, leading to the formation of galaxies. This process, predicted by inflationary models, has been corroborated by observations of the cosmic microwave background radiation, which show slight variations in temperature that match theoretical predictions. Another critical problem addressed by inflationary cosmology is the flatness problem. Observations indicate that the universe is remarkably flat, meaning that its total energy density is very close to the critical density required for a flat geometry. According to the Big Bang theory, without inflation, the universe's density would have to have been fine-tuned to an incomprehensible precision to result in the observed flatness. Inflation offers a solution by proposing that any initial curvature of the universe would have been ironed out by the rapid expansion, naturally leading to a universe that appears flat on large scales. Inflationary cosmology, since its inception by Guth, has undergone various refinements and faced numerous challenges. Yet, its core proposition of a period of rapid expansion early in the universe's history remains a cornerstone of modern cosmological theory. This revolutionary concept not only provides a framework for understanding the uniformity of the cosmic microwave background radiation and the formation of galaxies, but also addresses fundamental questions about the shape and texture of the universe itself. As the exploration of inflationary cosmology continues, with advancements in observational technology and theoretical modeling, this field remains at the forefront of unraveling the mysteries of our universe's origins and its grand architecture. The dawn of inflationary cosmology marked the beginning of a new era in the quest to understand the cosmos, offering insights into the profound processes that shaped the universe as we know it. The Big Bang theory stands as the predominant explanation for the universe's origins, a theory bolstered by a robust framework of evidence and observations. It posits that the universe began as an infinitely dense point approximately 13.8 billion years ago, expanding and evolving into the cosmos as it is known today. This theory is supported by several key observations that serve as its foundational pillars. Firstly, the cosmic microwave background radiation, CMB, plays a crucial role in corroborating the Big Bang theory. Discovered by accident in 1965, the CMB is the afterglow of the Big Bang, a faint cosmic background radiation that fills the universe. Its discovery provided a significant piece of empirical evidence supporting the idea that the universe began in a hot, dense state. Measurements of the CMB have shown that it is remarkably uniform across the sky, with slight fluctuations that correspond to the seeds of galaxies and large-scale structures observed in the universe. These measurements align with predictions made by the Big Bang theory and inflationary cosmology, solidifying the CMB's role as a cornerstone of our understanding of the universe's early moments. Another pillar of the Big Bang theory is the abundance of light elements, such as hydrogen, helium, and lithium, found throughout the universe. According to the theory, these elements were formed during the first few minutes after the Big Bang, in a process known as Big Bang nucleosynthesis. The proportions of these elements, particularly the ratio of hydrogen to helium, provide strong evidence for the Big Bang, as the observed abundances closely match those predicted by the theory. This agreement between observation and theory further validates the Big Bang as the mechanism behind the universe's formation. The role of dark matter and dark energy in shaping the cosmos is yet another critical aspect of the Big Bang theory. Dark matter, which does not emit, absorb, or reflect light, is thought to constitute about 27% of the universe's total mass and energy content. Its presence is inferred from gravitational effects on visible matter, such as the motion of galaxies within clusters. Dark energy, accounting for approximately 68% of the universe's total energy content, is believed to be responsible for the accelerated expansion of the universe observed today. These mysterious components of the universe, while not directly observable, significantly impact its structure and evolution, as predicted by the Big Bang Theory. The Big Bang Theory, supported by the evidence of the cosmic microwave background radiation, the abundance of light elements, and the enigmatic influence of dark matter and dark energy, provides a comprehensive explanation for the universe's origin and evolution. As observational techniques advance and theoretical models are refined, the understanding of these pillars continues to deepen, offering ever more insights into the cosmos' grand narrative. This exploration not only enriches the scientific understanding of the universe, but also underscores the profound interconnectedness of all cosmic phenomena, from the smallest atomic particles to the vast expanses of the intergalactic medium. In the quest to understand the universe's origins and its vast expanse, cosmologists were confronted with critical puzzles that the Big Bang Theory alone could not adequately address. These puzzles, notably the horizon problem and the flatness problem, played a pivotal role in the development of inflationary cosmology, a theory that proposes a period of rapid exponential expansion shortly after the Big Bang. The horizon problem arises from the observation that regions of the universe, billions of light-years apart, and thus seemingly never in causal contact, exhibit a striking level of uniformity in temperature and density. According to the standard Big Bang model, there would not have been enough time for light or any other signal to travel between these distant regions and equilibrate their properties. This presented a significant challenge. How could such uniformity exist across vast cosmic distances without any interaction? Inflationary cosmology offers a compelling resolution to the horizon problem. It posits that during the earliest moments of the universe, a brief but dramatic period of inflation expanded a tiny, causally connected region to a size far beyond what the Big Bang expansion alone could achieve. This rapid expansion could thus ensure that the entire observable universe originated from a region small enough to have reached a uniform temperature before inflation, explaining the observed isotropic nature of the cosmic microwave background radiation. The flatness problem is another conundrum that inflationary cosmology seeks to address. This problem involves the apparent fine-tuning required for the universe to have the flat geometry observed today. According to the Big Bang Theory, any initial curvature, positive or negative, in the universe's geometry should become increasingly pronounced as the universe expands. However, observations indicate that the universe is remarkably flat, suggesting that its density is very close to the critical density needed to achieve this flatness. Without a mechanism like inflation, the initial conditions of the universe would have had to be set to an implausibly precise degree to result in the observed flatness. Inflation offers a solution by proposing that the same rapid expansion that solves the horizon problem would also act to flatten the overall curvature of the universe. Just as a balloon appears less curved when inflated, the inflationary expansion would have diluted any initial curvature of the universe to near imperceptibility, naturally leading to the observed flat geometry without the need for fine-tuning. Furthermore, inflationary cosmology explains the formation of cosmic structures through the amplification of quantum fluctuations. During inflation, tiny quantum fluctuations in the density of the universe would have been stretched to macroscopic scales. These fluctuations then served as the seeds for the later formation of galaxies and large-scale structures. This mechanism provides a natural explanation for the origin of cosmic structure, linking quantum-scale phenomena to the large-scale structure of the universe. In sum, inflationary cosmology addresses some of the most profound puzzles in cosmology, offering elegant solutions to the horizon problem, the flatness problem, and the formation of cosmic structures. By proposing a period of rapid expansion early in the universe's history, inflation not only complements the Big Bang Theory, but also deepens our understanding of the universe's earliest moments and its large-scale structure. While inflationary cosmology has provided compelling solutions to some of the most significant puzzles in cosmology, it is not without its debates, challenges, and criticisms. Among the most pressing issues is the lack of direct observational evidence for inflation. Despite the strong indirect support from the uniformity of the cosmic microwave background, and the distribution of galaxies aligning with inflation's predictions, definitive proof of the inflationary epoch remains elusive. This gap in direct evidence has led to discussions about the falsifiability of inflationary models and whether they can be definitively proven or disproven with current or near-future observational capabilities. Another significant challenge is the fine-tuning problem, which inflation was initially proposed to solve regarding the universe's flatness and uniformity. However, critics of inflation point out that the theory itself requires fine-tuning of the initial conditions and parameters of the inflationary field to produce the observed universe. This has led to questions about the naturalness and simplicity of inflationary scenarios, with some in the scientific community calling for alternative explanations that do not require such precise initial settings. Looking forward, the future of inflationary cosmology research is vibrant and full of potential. One of the most promising avenues for providing direct evidence of inflation involves the detection of primordial gravitational waves. These ripples in space-time, generated during the inflationary epoch, would leave a distinct imprint on the cosmic microwave background polarization. The discovery of these primordial gravitational waves would not only serve as a smoking gun for inflation, but also open a new window into the physics of the early universe, offering insights into energy scales and processes far beyond the reach of current particle accelerators. Refining inflationary models is another critical area of future research. This involves developing a deeper theoretical understanding of the inflationary field, known as the inflaton, and its potential energy landscape. By exploring different models of inflation, scientists aim to make more precise predictions about the observable characteristics of the universe, which can then be tested against data from telescopes and cosmic surveys. This iterative process between theory and observation is crucial for narrowing down the vast landscape of possible inflationary scenarios to those most consistent with our universe. Advancements in observational techniques and technology will play a pivotal role in the future of inflationary cosmology. The next generation of cosmic microwave background experiments, large-scale structure surveys, and gravitational wave observatories promises to provide unprecedented precision in measurements of the early universe. These advancements not only have the potential to confirm the predictions of inflationary cosmology, but also to challenge them, possibly revealing new physics that could lead to a more comprehensive understanding of the cosmos. In conclusion, while challenges and debates surrounding inflationary cosmology persist, the continuous refinement of theoretical models, coupled with advancements in observational capabilities, holds the promise of uncovering new insights into the universe's earliest moments. The pursuit of direct evidence for inflation, particularly through the detection of primordial gravitational waves, stands as a beacon for future research, guiding the effort to unravel the mysteries of the cosmos' inception and evolution. Imagine a universe where the very essence of its vastness is composed of substances unseen, forces that bind galaxies together and propel them apart with relentless energy. This is not the realm of science fiction, but the reality of the cosmos, a reality where dark matter and dark energy play pivotal roles. Matter, the substance that forms everything observable, from the minuscule atom to the majestic spiral galaxies, has a counterpart that does not interact with light. This counterpart, known as dark matter, makes up about 27% of the universe. It is a form of matter that does not emit, absorb, or reflect light, rendering it invisible to current scientific instruments. The presence of dark matter is inferred from its gravitational influence on the rotation curves of galaxies. Without it, galaxies would not spin at the observed rates or maintain their current structures. The influence of dark matter extends to the very framework of the cosmos. It is the unseen scaffold upon which galaxies are built, its gravitational pull acting as the cosmic glue that holds these massive structures together. Without dark matter, the observed arrangements and distributions of galaxies across the universe would not be possible, and the current understanding of cosmic evolution would be fundamentally altered. In parallel with the enigmatic dark matter is another unseen force known as dark energy, which accounts for approximately 68% of the universe's mass energy content. Unlike the attractive nature of dark matter, Dark energy is a repulsive force, driving the accelerated expansion of the universe. This mysterious energy was first suggested by the observation of distant supernovae, which revealed that galaxies are moving away from each other at increasing speeds. This acceleration is a profound discovery that challenges pre-existing notions of a static or decelerating universe. The implications of dark energy are not merely confined to the expansion rate of the universe. They touch upon the ultimate fate of all cosmic existence. As galaxies are propelled apart by this unseen energy, questions arise about the future configuration of the universe and the potential for a cold, isolated cosmos. In laboratories and observatories across the globe, scientists are tirelessly working to unravel the properties of these elusive substances. Through experiments, such as those conducted in deep underground laboratories, or through observations made with high-powered telescopes and spacecraft, the scientific community is seeking to shed light on the dark constituents of the universe. Each discovery, each incremental piece of knowledge, brings humanity closer to comprehending the full picture of the cosmos and its mysterious dark components. The quest to understand dark matter and dark energy is more than an academic pursuit. It is a journey to grasp the fundamental nature of reality itself. The outcome of this scientific endeavor will redefine the boundaries of human knowledge and perhaps, one day, reveal the secrets held deep within the fabric of the cosmos. Astrobiology, a field that transcends traditional scientific boundaries, investigates life's potential spread throughout the universe. It merges biology, chemistry, geology, physics, and astronomy to comprehend life's emergence, its ability to endure in various environments, and where else it might exist beyond Earth. Astrobiologists scrutinize Earth's most inhospitable habitats to understand life's tenacity, delve into meteorites and cosmic dust to deduce life's building blocks, and probe exoplanet atmospheres for signs of life. The Mars 2020 mission, with the Perseverance rover on the forefront, exemplifies this quest by seeking ancient biosignatures on Mars. Although the mission does not search for current life forms, it meticulously gathers samples destined for Earth, promising a treasure trove of information upon their return. These samples will endure rigorous analysis, offering unprecedented insights into Mars' past habitability and potential life. Furthermore, education and outreach initiatives are integral to astrobiology's growth. Programs such as the Astrobiology Graduate Conference and the European Astrobiology Network Association (EANA) are pivotal in nurturing the next wave of astrobiologists. These platforms, alongside the Europa Clipper Intern Program, which engages students directly in research, emphasize the field's commitment to academic development and public involvement. Citizen scientists contribute to this endeavor too, participating in projects like the Planet Hunters NGTS, which seeks new exoplanets. Astrobiology's reach extends even to the icy expanses of Earth's poles, where digital models of research vessels like the RRS Discovery provide historical context to current scientific expeditions. These analog studies, such as the Amity mission for Analog Space Expedition, simulate extraterrestrial conditions, preparing for future exploration and potential discoveries. Through these multifaceted efforts, astrobiology not only seeks to answer the profound question of whether Earth's life is unique, but also inspires a collective pursuit of knowledge that transcends the confines of our planet. Astrobiology's essence is deeply rooted in its interdisciplinary approach. By interweaving the threads of biology, chemistry, geology, physics, and astronomy, it creates a tapestry that depicts the vast potential of life throughout the cosmos. This convergence of disciplines allows scientists to address the fundamental questions about life's origins and its ability to adapt and survive in the most extreme conditions. One of the most compelling aspects of astrobiology is the study of extreme environments on Earth. These environments, ranging from the scorching heat of hydrothermal vents deep within the ocean to the bone-chilling cold of the Arctic, serve as analogs for conditions on other planets and moons. By understanding how life not only survives but often thrives in these places, astrobiologists can better predict where to look for life beyond Earth and what forms it might take. These studies underscore life's incredible resilience and adaptability, traits that bolster the possibility of finding life in similarly harsh environments elsewhere in the solar system and beyond. The examination of meteorites and cosmic dust further contributes to the understanding of life's potential spread throughout the universe. These celestial materials are time capsules, harboring primordial substances from the dawn of the solar system. Analyzing their composition reveals the presence of organic compounds, such as amino acids, the very building blocks of life. Such findings suggest that the ingredients for life are not unique to Earth and may be dispersed throughout the cosmos, potentially leading to life in other worlds given the right conditions. These insights into extreme environments and cosmic materials not only inform the search for extraterrestrial life, but also enhance the understanding of life's beginnings on Earth. They provide a foundational knowledge that guides the exploration of other worlds, seeking environments where life as known, or perhaps entirely unknown, could exist. Through this interdisciplinary fusion, astrobiology does not just straddle multiple fields of study. It creates a holistic view of life in an ever-expanding universe, inviting contemplation on the origins and evolution of life across the cosmic expanse. The pursuit of extraterrestrial life has led to the development of key missions, each designed to peel back a layer of the unknown, inching closer to answering whether humanity is alone in the universe. One of the most significant of these missions is NASA's Mars 2020, which has placed the Perseverance rover on the Martian surface. Perseverance's primary goal is to seek signs of ancient life and collect samples that could provide definitive proof of past microbial activity on Mars. The significance of finding biosignatures of ancient life on Mars cannot be overstated. Such a discovery would transform the understanding of life in the universe. It would not only confirm that life developed on another world, but also suggest that life might be common in the cosmos, arising wherever conditions are favorable. The implications for astrobiology are profound. It would necessitate a reevaluation of the factors that contribute to the emergence of life and potentially lead to a deeper understanding of life's diversity and evolution. The Mars sample return missions represent the culmination of these exploratory efforts. The ambitious plan to retrieve the samples collected by Perseverance and bring them back to Earth for detailed analysis presents an unprecedented opportunity. With the full array of sophisticated instruments available on Earth, scientists will be able to scrutinize the Martian materials at a level of detail that is impossible with the equipment that can be sent to Mars. This level of analysis could reveal the molecular fingerprints of past life, offering definitive answers to questions that have intrigued humans for centuries. These missions are not merely exercises in scientific curiosity. They are critical steps in a journey that extends human understanding of biology, geology, and the potential for life beyond Earth. The prospects of what might be found in the Martian samples stir a sense of wonder and anticipation. Each finding, each piece of data collected, feeds into a larger narrative of cosmic exploration, where each planet and moon explored becomes a chapter in the unfolding story of life in the universe. The possibility of uncovering ancient Martian life and what it may reveal about life's universality propels astrobiology forward into an era of discovery that challenges the very notion of life's rarity and the conditions required for its existence. Astrobiology not only advances the frontier of scientific understanding, but also engages and inspires through education and outreach. The field's inherent intrigue captures the imagination, drawing people into a collective endeavor to explore the unknown. This fascination with life's cosmic potential has spurred a variety of educational initiatives and citizen science projects, democratizing the exploration of the universe. Educational events play a pivotal role in shaping the next generation of astrobiologists. The Astrobiology Graduate Conference, known as ABE GradCon, provides a dynamic forum for graduate students and early career scientists to share research, foster collaborations, and build a community within this interdisciplinary field. Similarly, the European Astrobiology Network Association EANA Conference brings together experts and enthusiasts from across the globe, promoting the exchange of ideas and the latest research findings. These events are crucial in cultivating a vibrant and diverse astrobiological community, ensuring the continued growth and innovation of the discipline. Citizen science, where interested individuals participate in scientific endeavors, has become an increasingly important aspect of astrobiology. Projects such as Planet Hunter's NGTS allow volunteers to sift through data from telescopes, identifying the subtle dimming of stars caused by transiting exoplanets. Such contributions have led to the discovery of new worlds and enhanced the understanding of planetary systems beyond our own. Furthermore, programs designed to involve students in astrobiology research, like the Europa Clipper Intern Program, offer invaluable hands-on experience. These programs connect academic learning with real-world applications, allowing students to contribute to the missions that may one day confirm the existence of life elsewhere in the solar system. Through these internships, students gain insight into the scientific process from hypothesis to discovery and the collaborative effort that underpins successful space exploration. Astrobiology's impact on education and outreach is a testament to the field's ability to inspire and engage. Whether through formal conferences that unite the scientific community or through citizen science initiatives that invite public participation, astrobiology fosters a sense of wonder and a desire to explore. By involving a diverse array of individuals in the search for life beyond Earth, astrobiology not only enriches the scientific community, but also ensures that the quest for understanding our place in the cosmos is a shared human experience. The vast expanse of the cosmos holds mysteries that have captivated humanity for centuries. Among these mysteries, black holes stand out as enigmatic celestial objects, warping the fabric of space-time and defying our understanding of physics. These cosmic giants, born from the collapse of massive stars, are regions of such intense gravity that not even light can escape their clutches. The boundary of a black hole, known as the event horizon, marks the point of no return. Beyond this threshold, the gravitational pull becomes insurmountable, trapping everything within its grasp. The event horizon is not a physical surface, but rather a theoretical boundary where the escape velocity exceeds the speed of light. In 2019, the Event Horizon Telescope captured the first ever image of a black hole, M87, located at the center of the Messier 87 galaxy, a massive elliptical galaxy approximately 55 million light-years away. This groundbreaking achievement provided a glimpse into the heart of a black hole, revealing its shadow against the backdrop of glowing gas. The image of M87 showcased a bright ring of light surrounding a dark central region. This ring, known as the accretion disk, is formed by superheated gas swirling around the black hole at incredible speeds. The intense gravitational pull of the black hole heats the gas to millions of degrees, causing it to emit radiation across the electromagnetic spectrum. One of the most intriguing aspects of M87 is the presence of powerful jets of plasma emanating from its poles. These jets, resembling lightsabers in their elongated, straight shape, extend for thousands of light-years into space. The origin and mechanism behind these jets have long been a subject of intense research. Scientists believe that the jets are powered by the black hole's powerful magnetic field. As gas falls into the black hole, it becomes entangled in the magnetic field lines. This interaction accelerates charged particles to near light speeds, creating the high-energy jets. The jets carry a significant amount of energy, equivalent to millions of times the energy output of our sun. Recent studies have revealed that M87 is losing a significant amount of energy through these lightsaber jets. This energy loss is a paradox, as black holes are generally thought to be efficient energy absorbers. The loss of energy could be attributed to the black hole's magnetic field, which might be slowing its spin and channeling energy into the jets. The energy loss phenomenon has implications for our understanding of black holes and their role in the evolution of galaxies. It suggests that black holes are not simply passive absorbers of matter, but can actively influence their surroundings through the powerful jets they produce. The study of black holes is an ongoing journey of discovery. With advanced telescopes and computational models, scientists continue to unravel the mysteries surrounding these enigmatic objects. The insights gained from studying black holes have profound implications for our understanding of gravity, space-time, and the fundamental laws of physics. As the pursuit of knowledge about black holes advances, the universe holds countless wonders waiting to be unveiled, and black holes remain at the forefront, of the quest to understand the cosmos. On June 25th, a milestone in space observation was achieved when the James Webb Space Telescope turned its near-infrared gaze upon Saturn, revealing a stark contrast between the darkened planet and the brilliance of its surrounding rings. This phenomenon is attributed to the presence of methane gas within Saturn's atmosphere, which absorbs sunlight at these wavelengths, casting the planet in shadow while allowing the rings to reflect light vividly. The image, a slice from the original capture, was part of an ambitious science program established to push the limits of Webb's observational capabilities. Among the objectives was to assess the telescope's ability to discern faint moons that orbit the gas giant and to provide a detailed analysis of Saturn's luminous rings, which have captivated astronomers and enthusiasts alike for centuries. A closer examination of the image reveals the subtle intricacies within Saturn's ring system. And if one looks attentively, the moons Dione, Enceladus, and Tethys make their presence known, despite the immense scale and brightness of the rings competing for attention. These natural satellites perform a celestial ballet around Saturn, governed by the immutable laws of gravitational dynamics, a dance now captured with unprecedented clarity through Webb's advanced imaging technology. The composition of Saturn's rings is a testament to the diversity found within the cosmos. The rings consist of a vast collection of particles ranging in size from those smaller than a speck of dust to colossal chunks comparable to earthly mountains. This assortment of rocky and icy fragments coalesces into the stunning halo that defines Saturn's unique appearance in the solar system. The collaborative effort behind this cosmic portrait brings together the expertise and dedication of numerous organizations and individuals, including NASA, the European Space Agency, ESA, the Canadian Space Agency, CSA, and the Space Telescope Science Institute, STSCI. Scientists such as Matt Tiscarino from the SETI Institute, Matt Hedman from the University of Idaho, Mariame El-Mutamid from Cornell University, Mark Showalter from the SETI Institute, Lee Fletcher from the University of Leicester, and Heidi Hamel from the Association of Universities for Research in Astronomy, IORA, have contributed to this endeavor. Furthermore, the image processing was adeptly handled by Jay DePasquale from STSCI, ensuring that every detail from the original data was meticulously brought to light. Together, these efforts have culminated in an image that not only challenges the boundary of what was previously visible, but also invites observers to ponder the mysteries that Saturn and its environs continue to hold. With the James Webb Space Telescope now operational, the solar system's planets and their intricate details are becoming more accessible, unveiling a universe ripe for exploration and discovery. Want to visit an interesting exoplanet or dip dangerously close to a black hole? It is not impossible. There's no law of physics that forbids humans from traveling through space, but it's just really, really hard. Here are some potential ways we could travel amongst the stars, ranked from least to most likely. Incredibly unlikely, faster than light travel. You can never travel faster than the speed of light. At least, that's what we understand through Einstein's special theory of relativity, the revolutionary theory that united space and time can become interchangeable. And while it might be easy to say that a future understanding of physics might do away with that restriction, it could be much harder to put it into practice. Special relativity is one of the most, if not the most, well-tested theories in all of physics. That's because special relativity isn't just a theory, it's a meta-theory. It's a set of instructions that help us build other theories of physics. Special relativity teaches us how space and time are connected in a fundamental way. The nature of this connection puts the speed of light as the ultimate speed limit. It's not just about light or even movement, but about causality itself. Special relativity lays out the fundamental groundwork for the relationship between past, present, and future. In other words, going faster than light allows for the possibility of going back in time, which does not appear to be allowed in our universe. Since all other modern physics theories are built on relativity, every time we test one of those theories, we're also testing relativity. While we could be wrong about the fundamental structure of space-time, the speed limit of light is unlikely to be dethroned anytime soon. Mostly unlikely. Wormholes. Wormholes could offer a path to the most distant places in the universe. These strange objects are a natural prediction of general relativity, Einstein's theory of how the force of gravity arises out of the bends and warps in spacetime. General relativity allows for wormholes by bending spacetime in a very peculiar way. But there's one small caveat. These objects are catastrophically unstable. The moment anything, even a single photon, tries to travel down the throat of the wormhole, it instantly tears itself apart. The only known way to stabilize a wormhole is by introducing a thread of exotic matter. This is matter that has negative mass, which, like time travel, does not appear to be allowed in the universe. It could be that our future descendants discover an alternative way to stabilize wormholes and allow for interstellar travel. But the amount of time it might take to uncover the necessary breakthroughs in physics might be longer than simply going to the stars ourselves. Highly unlikely. Generation ships. If we're stuck without shortcuts or loopholes in physics or other means to achieve FTL travel, then we're going to have to take our time. While sending a spacecraft traveling towards another star is not an issue of physics, it does pose loads of engineering challenges. One fanciful idea to travel among the stars is to build generation ships, large, slow-moving vessels where most of the passengers would never live to see their destination, living generation after generation as a self-contained city vessel that would eventually reach another star. Technically, humanity is already an interstellar species. Years ago, the Voyager 1 spacecraft traveled through the heliopause, the boundary of the solar system, and entered interstellar space. The good news is that it only took a few decades to achieve that feat. The bad news is that it's just getting started. Even at the incredible speed, at over 36,000 miles per hour, if Voyager 1 were headed in the direction of Proxima Centauri, which it is not, our nearest neighbor star at roughly 4.2 light-years away, it would take the spacecraft roughly 40,000 years to reach its destination. That number of years predates the development of the first cities and the advent of agriculture. So a generation ship isn't just a handful of generations, but hundreds of them, all needing to live self-sufficiently in the voids between stars, with no additional sources of water, fuel, food, or spare parts. Not impossible, but also highly unlikely. Mildly unlikely, really fast. To get to other stars faster, you can't have a giant lumbering ship. You instead need to be as small as possible. Rockets or other propellants would then get to higher speeds, making the journey as short as possible. Plus, at high speeds, the quirk of relativity helps out. Because of the constancy of the speed of light, movement through space is different than movement through time, and the faster an object advances in space, the slower it moves in time. As it approaches the speed of light, a year for the rest of the universe can shrink to months, days, or even minutes. Unfortunately, these effects only really kick in once an object progresses to more than 90% the speed of light, which is something humanity hasn't come close to achieving. But accelerating particles coming close to the speed of light is something that powerful events in the universe do on the regular, so it's definitely not impossible. But those are tiny particles, not comparatively massive spaceships. Pushing something like a human-sized craft to 90% the speed of light might require more energy than the sun produces in 1,000 years, but that is an engineering problem, not a physics one. Likely, we don't. In the far distant future, assuming that our current understanding of physics holds, at least as far as FTL travel and wormholes are concerned, humanity will likely send only a few scant missions to other stars and viable planets. But there's plenty of room here in the solar system, with hundreds of moons and thousands of asteroids to call home. It's a big enough place with plenty of mysteries to uncover. It is home, and there's no place like it. Moving beyond the seemingly insurmountable barrier of faster-than-light travel, this section examines other proposed methods for interstellar voyages. Wormholes, those tantalizing shortcuts through the fabric of space-time, offer a glimmer of hope, yet are beset by their own set of challenges, including catastrophic instability and the need for exotic matter. The concept of wormholes arises from general relativity, which allows for the bending of space-time in such a way that it could theoretically create a tunnel through the universe connecting two distant points. However, the stability of these structures is a significant hurdle, as they are prone to collapse the moment any matter attempts to pass through. The theoretical solution involves exotic matter with negative mass, but such matter does not appear to exist in our universe, making the practical realization of wormholes highly speculative. Generation ships represent a more grounded approach to the dream of reaching the stars. These massive, self-sustaining vessels are designed to support human life over centuries, carrying entire populations across the void of space. The concept of a generation ship addresses the vast distances and timescales involved in interstellar travel by creating a mobile society that could survive the journey to another star system. While the engineering and societal challenges of building and maintaining such a ship are daunting, the idea remains within the realm of possibility, anchored in the laws of physics as we understand them. The segment also explores the concept of achieving incredibly high speeds through conventional means. While not as fast as the speed of light, propelling spacecraft to a significant fraction of light speed could shorten the travel time to nearby stars to a more manageable scale, potentially within a human lifetime. This approach would rely on advancements in propulsion technology and energy generation, presenting its own set of engineering challenges. However, unlike faster-than-light travel or wormholes, this strategy does not require new physics, making it a more plausible option for the foreseeable future. Through these explorations, the vastness of space and the ingenuity required to traverse it are confronted. Each proposed method of interstellar travel presents unique challenges, from the theoretical and exotic to the practical and engineering-driven. Yet, the pursuit of these technologies reflects humanity's enduring desire to explore the unknown and reach beyond our solar neighborhood. Launched in the late summer of 1977, the Voyager spacecraft embarked on a monumental journey, one that would take them beyond the confines of the known solar system. Voyager 1 and Voyager 2, as they were named, were crafted with precision, and launched within weeks of each other, destined to explore the vastness of space. Powered by radioisotope thermoelectric generators, these probes were built to last, with a mission to relay unprecedented data back to Earth. The primary objective was clear: to study the outer planets, Jupiter, Saturn, Uranus, and Neptune. The intricacies of their atmospheres, magnetospheres, and the composition of their moons were of particular interest. As the spacecraft voyaged through space, they sent back detailed images and data that transformed humanity's understanding of the solar system. Significant among the trove of discoveries were the active volcanoes on Jupiter's moon Io, the intricate rings encompassing Jupiter, Saturn, Uranus, and Neptune, and the revelation of previously unknown moons orbiting these distant planets. Each finding challenged previous notions and opened new avenues of scientific inquiry. Perhaps one of the most groundbreaking discoveries was the heliosphere, a colossal magnetic bubble that encompasses our solar system and acts as a shield against cosmic rays. This discovery not only provided insights into the protective barriers of our solar system, but also raised questions about the interaction between solar winds and interstellar space. Navigating through the vast distances and harsh conditions of space, the spacecraft encountered and overcame numerous challenges. Despite exposure to extreme radiation and the gradual depletion of their power sources, both Voyager 1 and Voyager 2 have persevered, continuing their journey into the unknown reaches of interstellar space. Their resilience and longevity have allowed them to send valuable data back to Earth, contributing to an enduring legacy of scientific discovery and exploration. As these intrepid explorers travel further into the cosmos, they carry with them not only scientific instruments, but also a message intended for any potential extraterrestrial intelligence, a gold-plated record etched with sounds, images, and messages representing the diversity of life and culture on Earth. The journey of the Voyager spacecraft stands as a testament to human ingenuity and the unyielding quest for knowledge. It is a journey that transcends planetary bounds, venturing into the interstellar void with the hopes of answering some of humanity's most profound questions. As the Voyager spacecraft ventured deeper into the solar system, their trajectory brought them into close encounters with the giant planets, each encounter designed to propel them further using the gravity assist technique. This slingshot method, critical to the success of the mission, utilized the gravitational pull of the planets to significantly increase the speed of the spacecraft, altering their paths toward their next distant targets. The first monumental encounter was with Jupiter. As Voyager 1 and Voyager 2 approached this gas giant, their instruments captured detailed images of its turbulent atmosphere and its many moons. Among the most astonishing discoveries was the volcanic activity on Io, one of Jupiter's moons. This was the first time active volcanoes had been observed on another body in the solar system, providing valuable data about geological processes outside Earth. Next in their path was Saturn, renowned for its striking ring system. The Voyager's close flybys yielded unprecedented views of the rings and revealed intricate structures such as braids, kinks, and spokes, as well as the presence of numerous ringlets. This encounter not only enhanced understanding of the ring's composition and dynamics, but also led to the discovery of several new moons orbiting the planet. The journey continued to Uranus, where Voyager 2, in its unique trajectory, made its closest approach. The data returned revealed that Uranus had a markedly tilted magnetic field, unlike any other in the solar system. This was a surprising discovery, indicating complex magnetic processes at work. Additionally, Voyager's instruments identified 10 previously unknown moons and provided detailed images of the planet's rings, further enriching the scientific bounty returned from this distant world. The final planetary encounter was with Neptune. Voyager 2, the only spacecraft to visit this remote giant, transmitted back stunning images of the planet's vivid blue atmosphere and its dynamic weather patterns, including the Great Dark Spot, akin to Jupiter's Great Red Spot. The flyby also uncovered 6 new moons and 3 complete rings around Neptune, alongside intriguing hints of the planet's magnetic field and complex auroras. Each planetary encounter not only provided a wealth of data, but also demonstrated the ingenuity of using planetary gravity to steer the spacecraft across the solar system. This grand tour of the outer planets not only marked significant milestones in space exploration, but also left a lasting legacy, with the Voyagers continuing their journey towards the boundaries of the solar system and beyond. As they travel into interstellar space, the data they send back continues to challenge and expand the understanding of the solar system. Voyager 1 and Voyager 2, having completed their grand tour of the outer planets, embarked on perhaps the most groundbreaking phase of their journey, their voyage into interstellar space. This phase marked a significant milestone in human space exploration, as they became the first human-made objects to cross the heliopause, the boundary where the sun's solar wind is stopped by the interstellar medium. The crossing into interstellar space by Voyager 1 occurred on August 25, 2012, and it was a historic moment. As it crossed this boundary, it began to provide humanity with the first direct measurements of the density, temperature, and movement of the interstellar medium, the material found in the space between the stars. This data is vital for understanding the broader galactic environment in which the solar system resides. Voyager 2's crossing followed, occurring on November 5, 2018. Its entry into interstellar space provided a second point of data, crucial for confirming and expanding the findings from Voyager 1. The two spacecraft, now in slightly different locations in the vast expanse of space, continued to transmit data about cosmic rays and the interstellar magnetic field, offering unprecedented insight into the nature of the galaxy beyond the protective bubble of the heliosphere. The data sent back by the Voyagers has reshaped the understanding of the heliosphere's structure and its interaction with the interstellar environment. It revealed that the heliosphere is a dynamic, continuously changing bubble, heavily influenced by the interstellar wind. Observations of cosmic rays indicated that the heliosphere acts as a shield, reducing the number of high-energy particles from interstellar space that reach the inner solar system. The transition of Voyager 1 and Voyager 2 into interstellar space not only represents a monumental achievement in space exploration, but also underscores the vastness and the unexplored nature of space beyond the solar system. These milestones are not just waypoints, but are providing the fundamental data that challenges previous theories and enhances the understanding of the universe. As they journey further into the unknown, the legacy of the Voyager spacecraft continues to grow, driven by their ongoing transmissions from the edge of interstellar space. As the Voyager spacecraft ventured deeper into interstellar space, the challenges of long-distance space communication became increasingly apparent. One notable incident occurred when Voyager 1, now over 24 billion kilometers from Earth, began transmitting data that was unintelligible. This anomaly posed a significant challenge due to the immense distances involved, which meant that signals took nearly a whole day to travel from the spacecraft to Earth, and another day for commands to reach back. The issue was traced back to one of the 3 onboard computers responsible for packaging data before transmission. Engineers discovered that a single chip, crucial for storing part of this computer's memory, had failed. This malfunction caused the corruption of the data being sent, rendering it indecipherable. The situation highlighted the complexities of managing and troubleshooting a spacecraft so far from home, where direct intervention is impossible. To address this, NASA engineers devised an innovative solution. They reprogrammed the affected computer, tweaking the problematic code and breaking it into smaller sections. These segments were then stored in different parts of the computer's memory, ensuring they could still function cohesively when executed. This meticulous task required precise commands to be sent across the vast distance, each taking significant time to reach the spacecraft and take effect. On April 20, NASA confirmed that their modifications were successful, allowing engineers to restore meaningful communication with Voyager 1. This achievement not only solved the immediate issue, but also provided valuable insights into managing aging spacecraft systems under the challenging conditions of interstellar travel. This incident underscores the ongoing efforts to maintain the health and functionality of the Voyager spacecraft as they continue their journey into the unknown. The ability to adapt and innovate in the face of such challenges is crucial for the continued success of long-duration, deep space missions. As Voyager 1 and Voyager 2 push further into the cosmos, the data they return will help pave the way for future explorations, ensuring that the legacy of these pioneering spacecraft continues to inspire and inform. In the vast and enigmatic expanse of space, sounds exist in forms and frequencies beyond the common human experience on Earth. The detection and analysis of these sounds offer a unique perspective on the cosmos, revealing the dynamic processes that govern celestial bodies and phenomena. The NASA ESA ASI Cassini-Huygens spacecraft's encounter with Saturn's icy moon Enceladus unveiled a fascinating auditory phenomenon. The spacecraft's magnetometer instrument detected ion cyclotron waves, organized fluctuations in the magnetic field near Enceladus. These fluctuations provide insights into the electrically charged molecules present in the moon's atmosphere, offering a sonic representation of the moon's magnetic environment. Similarly, the Sun, a seemingly silent star from Earth's vantage point, produces low-frequency vibrations. These vibrations, recorded by the ESA NASA SOHO spacecraft, are the result of atmospheric circulation within the Sun, creating very low-frequency sounds. This auditory data allows scientists to study the internal processes of the Sun, enhancing understanding of solar dynamics. The Earth itself is a source of unique space sounds, as evidenced by the dawn chorus signals detected by ESA's cluster spacecraft. High-energy electrons trapped in the Earth's radiation belts produce these sounds when accelerated by the electromagnetic field. This phenomenon, akin to the chorus of birds at dawn, is a focus of study for understanding electron acceleration and its effects on the Earth's magnetosphere. Atmospheric phenomena also contribute to the symphony of space sounds. Whistler's electromagnetic emissions produced in the atmosphere have puzzled scientists since their first detection in the 19th century. Originating from thunderstorms, meteorites, or earthquakes, these sounds travel along closed magnetic field lines between hemispheres. Studying whistlers aids in understanding the Earth's atmosphere, ionosphere, and magnetosphere. The Cassini-Huygens spacecraft's journey through the gaps in Saturn's rings introduced another auditory element to the cosmic concert. Despite appearing empty, these gaps contain millions of dust particles. As the spacecraft traveled at approximately 70,000 kilometers per hour through these particles, the impacts were converted into sounds reminiscent of hail hitting a tin roof. Auroral phenomena produce another distinctive space sound. The auroral kilometric radiation, AKR, an intense radio emission from Earth, resembles the sounds of R2-D2 from Star Wars. Generated in the auroral zones, AKR serves as a remote indicator of geomagnetic activity. The Cluster spacecraft's wideband instrument recorded these sounds, facilitating the direct determination of AKR locations. Even the process of preparing spacecraft for their missions contributes to the collection of space sounds. ESA's Mars Express mission, for example, underwent vibration stress tests to ensure its instruments could withstand the rigors of launch. These tests produce auditory data that is crucial for mission success. Lastly, the Leonid meteors provide an auditory glimpse into meteor activity. As meteors cross Earth's atmosphere, they leave behind trails of ionized particles that reflect high-frequency radio signals. The motion of these trails, altered by upper atmosphere winds, creates a sound that can be heard before dispersing. This phenomenon provides valuable information on meteor paths and atmospheric conditions. Together, these diverse sounds from space form a cosmic concert that challenges earthbound conceptions of sound and silence, offering profound insights into the universe's complex and dynamic nature.